Our math skills for this week include the concept of molar mass. So we're going to be reviewing using molar mass a little bit and plugging it into our ideal gas law. And like we've talked about, N is our new variable representing amount of a gas within this equation. And we can only plug in moles into this equation. So our N is the amount in moles, but sometimes we will have grams that are reported because we can actually measure grams in lab from a balance. But we don't generally measure moles. We have to convert to moles in order to have useful information from grams. So we have a little review here. Our conversion factor, that 1 mole equals some amount of grams. And really, this one depends from element to element and compound to compound. So I'm just going to write molar mass like we did when we learned these mole conversions. And remember, that is on the periodic table. It is the average atomic mass for each element. If you have a compound, you will add up the sum, and that's the molar mass of all of the different elements involved. And if it's just a single element, you will report just that element's mass. And you can use it as a conversion factor. So for our math skills this week, most of these problems, actually all of these problems, are going to kind of 2 parts. One part, you will have to convert a mass into moles so that you can make sense of it into the equation and plug in the proper value. And then you will need to take those moles and actually use the ideal gas law of PV equals nRT to solve for the variable. So let's go ahead and do a couple of examples here using that review concept of molar mass as our conversion factor. So this one says, what is the mass? So we're finding mass, and keep in mind that mass is going to be representing N as well, but it has to be in moles, or it will be in moles per se, when we solve. So we want to know how many grams. Liters is relating to our volume, 7.5 liters of neon at 4.2 atmospheres and 300 Kelvin. When we solve this ideal gas law, we are going to be using the R value that corresponds to atmospheres, which would be 0.0821. So our first part of this problem will be solving the ideal gas law. So I'm just going to write it up here at the top so we can reference it throughout this whole worksheet. So we would have PV equals nRT, or sometimes I've heard teachers say PivNert, if that helps you to remember. Just kind of a silly word to remember the order of our ideal gas law. PV equals nRT. So let's plug in. 4.5 is our pressure, 7.5 volume. We don't know N. 0.0821 is R, and 300 is T. Do some multiplication, solving for N. Looks like we get 31.5 on this side and 24.63 on that side. So let's get N by itself, divide. .28, but remember, because we have solved the ideal gas law, this is in moles. So currently we have our answer in moles of neon, but our question asked for mass. So this is where we start part 2 of our problem. We have solved the ideal gas law. Now we need to convert it using a little train tracks friend. 1 mole of neon is the molar mass of neon from our periodic table. So if you don't have one handy, go grab a periodic table and look up neon. Its mass is 20.18. Okay, so So now we are ready to convert. Plug it in your calculator and you get 25.8 grams. So our answer, 25.8 grams of neon. Lastly, we need to check for our significant figures. 300 Kelvin is one significant figure, so we'll make this 30. Round that up. Ta-da! And there's our answer. So like I said, you'll have to do 2 steps. You'll need to convert using molar mass at some point, and you'll need to plug into the ideal gas law for each of these problems in our math skills, because we are finding grams. So number 2 is very much like number 1. So I'm going to leave that one for you to do, but you have a different pressure value, so you'll be using a different R value. Number 3 is the exact same process. I believe this one does not give you, number 3 has an issue. It needs to give you the compound. Otherwise, you won't be able to use molar mass. So our compound is NH3. And I did send an email out about that. So if you check that, it has some other typos from the week. But that's one of them. Information that was not fully complete. Okay, so on the back side, or our next page here, page 8, now we have, again, the 2 steps, but we're going to be solving for a different variable than n. However, our n value is given in grams, so we'll have to convert first to moles and then be able to plug it in to our ideal gas law. So let's go ahead and assign all of our variables. It says, what is the volume in liters of 84.2 grams CO2, 290 Kelvin, and 1.5 atmospheres. So that means we're using 0.0821 as our R value. Now, this should be giving you red flags because you cannot plug in grams to the ideal gas law, so we have to start with our conversion. So 84.2 grams, let's convert grams carbon dioxide using our periodic table. So add up a carbon and 2 oxygens to give us that molar mass, which is 44.01, and that will give you 1.91 moles. So now we have the correct value to be able to plug in to our equation. We have to put moles into N. We cannot put grams in. If you were to put grams, 84.2, your number would be ginormous because it would make you, it's thinking that you're saying 84.2 moles because of the ratio of the units for our R value. Remember, this is representing 0.0821 atmosphere, liter, mole, Kelvin. That's its unit. And so we have to use moles when we're plugging in and using this R value. There is no R value with grams. So let's plug our values in now. We've got P, we've got V. Actually, we don't have V, but we will leave the letter V there so we can solve for it. N, R, and T. And now we do some math to solve our problem. So it looks like we got 1.5 V equals 45.58. Let's solve for V by dividing, and our V is 30.3. So there's 30.3 liters of carbon dioxide. And let's just check our units for significant figures. Looks like we need to have 2 sig figs. So this is 30, and I'll leave the decimal there so that we know the 0 is made significant. So 30 liters of carbon dioxide. There's our volume. 5, 6, and 7 are similar to number 4. 4, where you will have grams given to you and you need to convert it to moles before plugging in. So let's do number 6 together, and then you can do the rest. So our last one says, if a 15.2 gram sample of helium at standard temperature fills 25 liters, what is its pressure in kPa? So we know 15.2 grams will eventually be N, but we need to convert it before we can put it into our equation. We've got volume, we don't know pressure, but we know we want it in kPa, which tells us our R value needs to be 8.31. And standard temperature is 273 Kelvin. Remember, that's 0 degrees Celsius. So add 273 and we have the temperature. So let's do our conversion first to get moles for helium. So grams helium, we need its molar mass from the periodic table, which is 4.00. If we solve this, we get 3.8 moles of helium. So that is the value we want to plug in for N. And now we can plug and chug into our equation. We don't know P. We do have V and all the rest. And R T multiply 25P equals, this is a large number, 8,610. Solve for P, 344. Beautiful. And we're going to need 2 significant figures here in our answer, so 340 kPa. Here's the pressure. Find moles, then plug it in. If you're finding the mass, then you'll plug it in and then convert to grams. That was for number 1, 2, and 3 if you're finding the mass. Number 7 says you choose the unit for pressure, so it'll be a lot like number 6, but you can either use kPa, which will give you one R value, or you can use atmospheres, which you'll use a different R value. You get to choose for number 7.